Hello students, in this video we'll discuss properties of the roots of orthogonal polynomials. Let's be given a collection of orthogonal polynomials phi 0, phi 1, phi n on the interval AB with respect to the weight w of x strictly greater than 0, okay? And let's make some observations now. So the first observation we're going to make is that when we integrate the integral from a to b of phi n of x, phi 0 of x, w of x, dx, we have to get 0 because phi n and phi 0 are orthogonal to each other. Now phi 0 is just a constant, right? So that's just a constant. C, which we can pull out of the integral, right? Which says that, and this is greater than 0, and so that says that phi n has to change signs, because if it integrates, if it was always greater than 0, and say, for example, that, let's suppose without loss of generality that C is greater than 0, right? So if C is greater than 0 without loss of generality, then that would say that phi n has to be both positive and negative for it to have a 0 integral on that interval over there, right? So in other words, phi has to alternate signs, so phi n alternates signs. And that implies that phi n has a root in AB. Excellent. So I know that phi n has at least one root in AB, right? Now what I'm going to do is the following. So let's let alpha 1, alpha 2, alpha L be the roots of phi n with odd multiplicity. Okay? And let's suppose that L is strictly less than n, right? Okay? Then what can we do? Then the integral from a to b of phi n, and then x minus alpha 1, x minus alpha 2, x minus alpha L, right? Okay, this is a polynomial, of course, of degree L, less than n, right? W of x dx. And so this integral over here has to be 0 because I know that phi n is orthogonal to polynomials of degree L, because L is less than n, right? But now, of course, what's happening over here? So now, if I can pull out, I have an x minus alpha 1, and so does phi n as an x minus alpha 1, right? So in other words, the parity of this root over here at alpha 1, this is an odd parity over here. There's an odd parity over here embedded in the phi n. So this x minus alpha in the overall expression has an even parity over here. So there's going to be an even parity over here of alpha 1. There's going to be an even parity of alpha 2, even parity of alpha n. And so what happens is this thing, phi n, what? Well, what would happen? This is going to be 0, but this thing is always not greater than or equal to even parity, even parity, even parity, even parity, greater than 0, right? So this thing has, by construction, this integral will be something of even parity. So the integral phi n of x, x minus alpha 1, x minus alpha L dx is greater than 0, and that's a contradiction. And that implies that L is equal to n, and that tells me what? That tells me that this, the roots of phi n, I have alpha 1 through alpha L, there's n roots, and they're all of what? They're all of odd multiplicity, which means they have to be simple roots, right? And alpha 1 through alpha n are simple roots. Excellent. Let's get a little more leverage out of this. In other words, the roots of an orthogonal polynomial on the interval a to b are all the phi n, the nth orthogonal polynomial has n real roots, and they're all simple. Excellent. All right, good. What's the consequence of this? A consequence of this is that the roots, so corollary, the roots, so phi n, and the next one, share no common roots. Okay. And how do I prove this? I can use sort of the same sort of reasoning over here. So a consequence of this is that we know that phi n minus any constant sigma, phi n minus 1, this thing over here, is going to be what? If this is perpendicular, we'll have n simple roots for any sigma in R. Okay. Now, of course, how do we prove something like this? How do we prove this statement over here? This polynomial over here. That polynomial over there is going to be what? This thing is going to be perpendicular to what? This is going to be perpendicular to phi n minus 2, phi n minus 3 all the way down to phi 0, and I can run exactly the same argument, because in other words, this x minus alpha L, the real restriction is that its L is going to be less than or equal to n minus 2, right? Because if there's a quadratic root, the quadratic root is an even parity thing, so I can't jump from 2 to 3, I can only jump from 1 to another 1, so in other words, this is a restriction. I can actually get one sort of level down from this by using that argument again, by just running the same exact argument, right? Okay. Has simple roots and as n simple roots, right? So let's suppose, so here's the proof of the corollary. Proof, suppose phi n of zeta was equal to phi n plus 1 of zeta and equal 0, like so, okay? Then we know that phi n prime of zeta is not equal to 0, and phi n plus 1 prime of zeta is not equal to 0 by the fact that they're simple roots, right? And then what I can do is this. Then I'm going to let sigma, I'm going to construct a function h over here. H of x is going to be phi n plus 1 minus the phi n plus 1 prime of zeta over phi n prime of zeta. That's a constant now, phi n. So this, of course, is going to be my sigma over here, right? Then what do I know? I know that if I plug in, I know that h has what? H is going to have n plus 1 simple roots, right? So h only has simple roots. Okay. H only has simple roots, but what's h of zeta? H of zeta is going to be 0. And h prime of zeta is going to be what? Well, it's going to be equal to 0 also. So that's a what? That's a contradiction, because I've shown that h has a root zeta that's not a simple 0. That's a contradiction. So the assumption that phi n of zeta and phi n plus 1 of zeta were equal to 0 simultaneously has to be false. In other words, the roots of orthogonal polynomials are, from one level to the next, cannot coincide. They have to be different. In a further video, we're going to actually show that the roots start to interlace, right? So if I plot out the roots of phi n plus 1, then the roots of phi n have to be in between the roots of phi n plus 1, sort of similar to the behaviors of roots of derivative, the roots of a function and the roots of its derivative. So we'll prove that interlacing theorem in a further video. Thank you very much.